Right now, 22,000 light-years from where you sit, there exists a region of space so violent that every law of physics you understand becomes a weapon pointed directly at you. At the centre of our galaxy lurks a supermassive black hole 4 million times more massive than our Sun. Sagittarius A does not simply exist, it devours. It shreds stars into streams of plasma. It warps time itself until seconds become centuries. It bathes everything within light years in radiation intense enough to strip atoms apart. The galactic centre is not a destination. It is an execution chamber operating on a cosmic scale. No shielding can protect you. No engine can escape once you cross the threshold. This is not speculation. This is physics. And physics at the galactic centre has one absolute rule. Nothing survives. If you want to understand why humanity must never attempt this journey, hit that like button and subscribe. Prepare yourselves, we begin. Right now, 22,000 light-years from where you sit, there exists a region of space so violent that every law of physics you understand becomes a weapon pointed directly at you. At the centre of our galaxy lurks a supermassive black hole 4 million times more massive than our Sun, Sagittarius. A star does not simply exist, it devours. It shreds stars into streams of plasma. It warps time itself until seconds become centuries. It bathes everything within light years in radiation intense enough to strip atoms apart. The galactic centre is not a destination. It is an execution chamber operating on a cosmic scale. No shielding can protect you. No engine can escape once you cross the threshold. This is not speculation. This is physics. And physics at the galactic centre has one absolute rule. Nothing survives. If you want to understand why humanity must never attempt this journey, hit that like button and subscribe. Prepare yourselves. We begin. 22,000 light-years from Earth, space-time ends. Not metaphorically, not eventually. It ends at a mathematical boundary where the equations governing reality produce infinities and contradictions. This boundary surrounds an object called Sagittarius, a star, and it represents the point beyond which the universe stops making sense. 4 million solar masses compressed into a region smaller than Mercury's orbit. That is what a star is. To understand this scale, imagine taking 4 million stars identical to our Sun and crushing them down until they occupy less space than the distance between Earth and its nearest planetary neighbour. The density becomes meaningless. The gravitational pull becomes absolute. The event horizon, the boundary of no return, stretches roughly 12 million miles across. That sounds enormous until you realise light itself, travelling at 186,000 miles per second, cannot escape once it crosses this threshold. Photons, the fastest thing in the universe, get trapped, pulled inward, erased. Gravity at this scale does not pull, it commands. Space-time curves so sharply near the event horizon that all paths, every possible trajectory, point toward the singularity at the centre. Move forward, you fall in. Move backward, you fall in. Move sideways, you fall in. The geometry of space itself becomes a funnel with only one direction. Down. Here is what that means for anything approaching. At a certain distance, roughly a few 100 million miles out, tidal forces begin to matter. Gravity pulls harder on the side of your spacecraft facing the black hole than on the side facing away. The difference is small at first. Instruments detect it before crew members feel it. But as distance decreases, the differential grows exponentially. At 10 million miles, structural stress becomes measurable. Metal begins to groan. At 5 million miles, hulls start to deform. Rivets pop. Seams split. At 2 million miles, molecular bonds break. The spacecraft does not crumble. It stretches. Every atom on the near side experiences more gravitational acceleration than atoms on the far side. The object elongates like taffy being pulled. This is not a slow process. Once tidal forces exceed material strength, disintegration happens in seconds. A spacecraft becomes a stream of debris. That debris becomes a stream of molecules. Those molecules become a stream of atoms spiraling into the black hole at a significant fraction of light speed. But the black hole itself is almost gentle compared to what surrounds it. Therefore, the event horizon marks the boundary where matter disappears from the universe entirely. But the region outside that boundary, the space where matter still exists before crossing over, is where the true violence occurs. Astronomers call this region the innermost stable circular orbit. Below this distance, nothing can maintain a stable path. Everything either escapes or falls in. There is no middle ground. For Esquerra's star, this boundary sits roughly 75 million miles from the event horizon. Anything closer enters a zone where orbital mechanics break down. Velocity required to maintain orbit approaches light speed. But reaching light speed requires infinite energy, which is impossible. Therefore, objects spiral inward, accelerating continuously, heating from friction within falling gas until they glow white hot and then vaporize. The black hole does not need to touch you to kill you. Its gravity well is so deep that simply being near it dooms anything with mass. This is the monster at the center, a 4 million solar mass execution machine that has been operating for billions of years, grinding stars and gas clouds into radiation and gravitational waves. We have observed stars orbiting Esquerra's star, massive stars, dozens of times heavier than our Sun, whipping around the black hole at speeds exceeding 5,000 miles per second. Their orbits are elliptical, bringing them within a few light hours of the event horizon at closest approach. These stars survive only because they do not cross the innermost stable orbit. They skim the edge of destruction and swing back out. But their survival is temporary. Eventually tidal forces will strip away their outer layers. Eventually they will lose enough mass to fall below the threshold. Eventually Esquerra's star will consume them. Dozens of stars have already died this way. We see their remains in the form of high-velocity gas clouds stretched into bizarre shapes, elongated ribbons of matter spiraling inward. One such cloud, designated G2, passed within 15 billion miles of the event horizon in 2014. Astronomers predicted it would be torn apart and consumed. They were half right. The cloud stretched, heated, and partially disintegrated. But some of it survived, continuing its orbit as a shredded remnant of what it once was. If a gas cloud barely survives, a solid object has no chance. The black hole is patient. It does not chase prey. It simply exists, and existence alone is enough. Gravity reaches across light years, pulling everything nearby into inevitable trajectories. Some objects fall quickly, others take millions of years. But all roads lead to the event horizon. This is the executioner. This is the reason the galactic center is forbidden. But the black hole, terrifying as it is, represents only the most obvious threat. Therefore, understanding Esquerra's star is just the beginning. Because the space surrounding it is filled with something far worse than gravity alone. Radiation. The galactic center glows, not with the gentle light of distant stars, but with a shriek of high-energy radiation that would cook matter down to its constituent particles in seconds. X-rays, gamma rays, cosmic rays accelerated to 99.9% of light speed. This is not an environment. This is a radiation furnace operating at intensities that make nuclear reactors look tame. SGR-A star itself emits relatively little radiation when dormant. The black hole is currently in a quiet phase, accreting matter slowly. But quiet is relative. Even in its calm state, the region within a few light years radiates more X-ray energy per second than our Sun produces across all wavelengths in a year. When the black hole feeds actively, consuming a gas cloud or shredded star, that output increases by factors of millions. The mechanism is simple. Physics turned monstrous. Matter falling toward the event horizon accelerates. Friction between particles heats the infalling material to tens of millions of degrees. At these temperatures, atoms are fully ionized, electrons stripped away, nuclei exposed. The resulting plasma emits blackbody radiation that peaks in the X-ray spectrum. This radiation does not radiate outward gently. It blasts outward in all directions with enough energy to ionize gas clouds dozens of light years away. But X-rays are just the beginning. Magnetic fields near Esquerra's star, twisted and amplified by the rotating accretion flow, accelerate charged particles to relativistic speeds. These particles, primarily protons and heavier atomic nuclei, become cosmic rays. When they slam into other particles or magnetic field lines, they emit gamma rays through a process called inverse Compton scattering. The gamma rays carry energies measured in billions of electron volts. A single gamma ray photon from the galactic center contains more energy than 100,000 visible light photons combined. What does this mean for matter? At the molecular level, High-energy radiation is a demolition tool. X-rays have enough energy to knock electrons out of inner atomic shells. This creates cascades of secondary electrons that ricochet through surrounding material, ionizing everything they touch. DNA molecules shatter, chemical bonds break, proteins denature. Within seconds of exposure, biological tissue becomes a soup of disconnected atoms. Shielding does not help at these intensities. Radiation shielding works by placing mass between the source and the target. Lead, water, polyethylene, all absorb radiation by forcing photons and particles to interact with atoms in the shielding material. But there are limits. For every inch of lead, X-ray intensity drops by roughly half. That sounds effective until you calculate the thickness required. At the galactic center, X-ray flux exceeds Earth's background radiation by factors of trillions. To reduce that flux to survivable levels would require lead shielding hundreds of feet thick. The mass becomes prohibitive. A spacecraft wrapped in that much lead could not accelerate, could not maneuver, could not function. And even if you built such a ship, gamma rays would penetrate anyway. Gamma rays interact so weakly with matter that they pass through feet of lead with minimal attenuation. Stopping them requires yards of shielding, tons upon tons of mass, but the radiation environment gets worse the closer you approach. Within 1 light year of Escura star, the cosmic ray density increases by factors of thousands compared to Earth's neighborhood. These are not the relatively low-energy cosmic rays that strike Earth's atmosphere. These are particles accelerated to energies approaching the theoretical maximum allowed by physics. When such a particle strikes matter, it does not just ionize atoms, it triggers nuclear reactions, atomic nuclei fracture, neutrons spray outward, secondary particles create their own cascades. The effect on solid matter is insidious. Cosmic ray bombardment creates defects in crystalline structures. Metals become brittle. Semiconductors fail as radiation-induced defects accumulate in their lattices. Over days or weeks, spacecraft systems degrade. Computer memory corrupts. Sensors drift out of calibration. Structural components develop microfractures that propagate until catastrophic failure occurs. Therefore, any journey toward the galactic center becomes a race against radiation damage. The spacecraft disintegrates before it arrives. Systems fail before the mission completes. Crew members, if any are foolish enough to attempt this, accumulate lethal doses of radiation long before reaching the innermost regions. Magnetars orbiting near Escura star make the problem exponentially worse. Magnetars are neutron stars with magnetic fields trillions of times stronger than Earth's. Several have been detected within a few light years of the galactic center. Their magnetic fields accelerate particles and twist space itself in ways that amplify radiation output. When a magnetar flares, and they flare unpredictably, it releases more energy in 1/10 of a second than our sun emits in 100,000 years. That energy emerges as gamma rays and X-rays. A magnetar flare at 1 light-year distance would deliver a radiation dose equivalent to standing at ground zero of a nuclear detonation. Except instead of lasting milliseconds, the radiation continues for minutes. There is no shelter, no bunker thick enough. The photons penetrate everything. Astronomers have observed magnetar flares from the galactic center. In 2013, one such event was detected across multiple wavelengths. The burst lasted 14 seconds and reached Earth as a measurable spike in X-ray detectors, despite traveling 22,000 light-years. At the source, the intensity was beyond calculation. Anything within a light-year would have been sterilized. Anything within a light month would have suffered catastrophic radiation damage. The radiation hell surrounding Escura star is not hypothetical. It is measured, it is documented, it is absolute. No amount of engineering can protect against it because the energies involved exceed what materials can withstand. Atoms themselves become unstable. Molecules cannot maintain their bonds. Matter breaks down into component parts under the relentless bombardment. But even if you somehow built a spacecraft from neutronium, the densest stable matter in the universe, and wrapped it in magnetic fields strong enough to deflect cosmic rays, the radiation would still doom you. Because radiation is not the only killer. Therefore, while your ship's hull cooks under X-ray bombardment and cosmic rays shred your electronics, gravity begins its work. And gravity at the galactic center does not kill quickly. It kills precisely, methodically, by pulling you apart one atom at a time. Gravity does not crush. Not at the galactic center. It stretches. It pulls. It separates matter into threads so thin that molecules cannot hold together. This process has a name that sounds almost whimsical until you understand what it means: spaghettification. The principle is simple. Gravity weakens with distance following an inverse square law. Double the distance, gravity drops to 1/4 strength. This relationship holds everywhere in the universe. But near Esquerra star, distances become so compressed and gravitational gradients so steep that the difference in pull between 2 points just feet apart becomes lethal. Imagine a spacecraft 10 meters long approaching the black hole. The front end, closer to Esquerra star, experiences stronger gravitational acceleration than the rear end. At a distance of 1 million miles from the event horizon, this difference is negligible. A few microgravities. Instruments detect it, but structure handles it easily. At 500,000 miles, the differential reaches 1/10 of Earth gravity. Metal groans, joints stress. At 100,000 miles, the difference exceeds 10 Earth gravities. The spacecraft begins to elongate. Rivets shear, welds crack. At 10,000 miles from the event horizon, the tidal force becomes catastrophic. The front of the spacecraft experiences gravitational acceleration hundreds of times stronger than the rear. Steel stretches like rubber. Bulkheads collapse inward on one end while being pulled outward on the other. The ship does not break cleanly. It deforms. Compartments telescope into each other. Structure that was rigid becomes plastic, then liquid in behavior. But spacecraft are robust compared to biological matter. A human body approaching Esquerra star would experience tidal forces across its length. At sufficient proximity, the gravity pulling on your feet would exceed the gravity pulling on your head by thousands of Gs. Your body cannot withstand this. Bones are strong in compression but weak in tension. Ligaments tear, vertebrae separate, blood vessels rupture as pressure differentials rip them apart. The process accelerates as distance decreases. At 1,000 miles from the event horizon, tidal forces across a human body would exceed 100,000 Gs. You do not die from this. You disassemble. Cells separate from each other. Tissues pull apart at the molecular level. What was a body becomes a stream of organic molecules stretched into a line kilometers long, but only atoms wide. This is not instant. The process takes seconds, perhaps as long as a minute depending on your velocity and trajectory. Consciousness would not survive it, but the matter that was you continues falling, stretching thinner and thinner. Molecules break into atoms. Atoms ionize under the stress and radiation. Eventually, what remains is a thread of plasma spiraling into the event horizon. Astronomers have observed this process happening to stars. In 2014, telescopes detected a gas cloud designated G2, making a close pass by Esquerra star. Predictions suggested the cloud would be torn apart by tidal forces. Observations confirmed it. The cloud, originally roughly 3 Earth masses of gas, stretched into a filament over 100 billion miles long. One end of the filament was already falling into the black hole while the other end was still approaching. The cloud became a bridge of matter spanning a distance greater than our entire solar system. G2 was diffuse gas, loosely bound. A solid object suffers worse. The Roche limit defines the distance at which tidal forces overcome an object's self-gravity. For a human body orbiting Esquerra star, the Roche limit sits roughly 40,000 miles from the event horizon. Closer than this, your body's gravity cannot hold itself together against the tidal stress. You come apart not from external force, but because gravity pulling your feet toward the black hole exceeds the gravitational attraction between your feet and your head. This is the elegant horror of tidal forces. The universe does not need to apply external stress. It simply creates a situation where different parts of you want to be in different places, and the forces holding you together are insufficient. You dissolve. For spacecraft, the Roche limit depends on structural strength rather than self-gravity. Steel has tensile strength measured in hundreds of megapascals. At roughly 200,000 miles from Esquerra star, tidal stress exceeds steel's tensile strength. The spacecraft does not orbit, it fragments. Pieces separate and fall independently, each piece stretching and fragmenting in turn. No material can withstand this indefinitely. Diamond, the hardest natural substance, has higher tensile strength than steel. But even diamond has limits. Carbon bonds can only sustain so much stress before they break. At perhaps 150, would exceed diamond's strength. The bonds would snap. The crystal lattice would shear apart. Exotic materials fare no better. Carbon nanotubes, among the strongest materials ever synthesized, might survive to 100,000 miles. Neutronium, matter compressed to neutron star densities, might survive to 10,000 miles, but nothing survives to the event horizon intact. Tidal forces grow without bound as you approach. At some point, every material fails. Therefore, the black hole ensures that everything entering it arrives as a stream of particles, not as coherent objects. Structure cannot survive. Ships become debris. Debris becomes molecules. Molecules become atoms. Atoms become plasma. The event horizon swallows only the most basic constituents of matter, because gravity has already disassembled everything else. But tidal forces represent only one aspect of the gravitational trap. The other aspect is more subtle and perhaps more terrifying. Gravity near Segura star does not just pull matter apart, it traps trajectories. Once you fall below a certain distance, escape becomes impossible, not because you lack thrust, but because space-time geometry itself forbids it. The photon sphere sits 1.5 times the radius of the event horizon. At this distance, 18 million miles from the center of Segura star, gravity is strong enough to bend light into closed orbits. Photons can circle the black hole indefinitely, neither escaping nor falling in. For massive objects with slower velocities, the equivalent boundary sits farther out. Below this distance, no amount of thrust allows escape. You can fire your engines at full power continuously, and you will still fall inward. Space-time curvature is too steep. Every possible trajectory curves back toward the event horizon. This creates a psychological trap as horrifying as the physical one. Imagine realizing you are falling, and that no action you take matters. Engines fire, fuel burns, thrust vector changes. None of it helps. You watch the event horizon grow larger in your viewport, and there is nothing you can do. Physics has locked you into a trajectory that ends in annihilation. But even escaping the photon sphere does not guarantee survival, because the region around the black hole is not empty space. Therefore, while tidal forces stretch matter and gravitational wells trap trajectories, the environment between you and Segura star is filled with obstacles. Millions of stars crowd into a volume of space smaller than the distance between the Sun and its nearest neighbor. This density makes the region around the black hole not just gravitationally deadly, but kinetically lethal. You're about to enter a war zone where stars themselves are the bullets. 5 million stars occupy a sphere just 10 light-years across. To understand this density, consider that the nearest star to our Sun sits 4 light-years away. In our neighborhood, stellar density is roughly 1 star per 30 cubic light-years. At the galactic center, density exceeds 1 star per cubic light-year. In the innermost regions, density reaches 1 star per 100th of a cubic light-year. Stars are separated by light months, not light years. In some zones, stellar spacing drops to light weeks. This crowding transforms the galactic center into a collision zone. Stars do not sit still. They orbit Segura star at velocities ranging from hundreds to thousands of miles per second. Their orbits cross, their paths intersect, and occasionally, inevitably, they collide. Stellar collisions are not gentle. When two stars traveling at 1,000 miles per second meet, the kinetic energy released exceeds anything nuclear fusion can produce over millions of years. The stars do not bounce, they interpenetrate. Plasma from one star plows into plasma from the other at supersonic speeds, creating shock waves that heat material to hundreds of millions of degrees. The collision triggers runaway fusion reactions. Elements heavier than iron, normally impossible to create through stellar burning, form in seconds as neutrons flood through the colliding matter. The result is a titanic explosion, not a supernova, but something almost as violent. The merged stars blast material outward at thousands of miles per second. Gas clouds expand into surrounding space, plowing through the interstellar medium and triggering compression waves. These waves can collapse nearby gas clouds, triggering new star formation even as the collision destroys the original stars. Astronomers estimate that stellar collisions near Segura star occur every 10,000 to 100,000 years. That sounds rare until you consider the volume involved. Within 10 light-years of the black hole, collisions are ongoing. Somewhere in that volume at any given moment, stars are merging. The radiation from these events floods the region. X-rays spike, gamma rays surge, the blast waves propagate outward at significant fractions of light speed. For anything in the vicinity, these collisions are extinction events. A collision occurring 1 light-year away releases enough radiation to sterilize planets dozens of light-years distant. The prompt gamma ray burst alone would deliver lethal doses to any biological matter within months of light travel. The X-ray afterglow continues for years, maintaining lethal radiation levels across light years of space. But collisions are not even the primary danger from stellar density. The greater threat is navigation. Flying through the galactic center is like flying through an asteroid field, except the asteroids are stars and the spaces between them are measured in light months instead of miles. At relativistic speeds, even these distances become hazards. A spacecraft traveling at 10% light speed covers 1 light month in 10 months. That sounds like ample warning time to avoid stars, but space is three-dimensional. Stars move, orbits precess. Trajectories change as gravitational perturbations from nearby stars alter paths. What appears to be a clear corridor when you begin your journey might contain a star by the time you reach that point. Calculating safe trajectories requires knowing the positions and velocities of every star in the region with extreme precision. Near S-Gray star, gravitational interactions are so complex that 3-body problems become million-body problems. Predicting where any given star will be more than a few years in advance becomes impossible. Chaos dominates. Small uncertainties in initial positions amplify into large uncertainties in future locations. Therefore, navigation through the galactic center cannot be planned far in advance. It must be reactive. Course corrections must happen continuously as new data arrives. But light speed delay creates problems. If a star 1 light month away changes trajectory, you will not know for 1 month. By the time the information reaches you, the situation has changed again. You're always navigating based on outdated information. The stellar density also creates gravitational chaos. Every star exerts gravitational pull. Near S-Gray star, thousands of stars contribute significant gravitational acceleration to any object passing through. The combined effect is a gravitational field that changes rapidly over short distances. Trajectories bend unpredictably. What should be a smooth hyperbolic orbit around the black hole becomes a chaotic tumble as stellar gravity perturbs your path. This makes powered flight through the region nearly impossible. Engines must fire almost continuously to maintain any desired trajectory. Fuel consumption becomes prohibitive, and every course correction must account for gravitational pulls from dozens of nearby stars, each moving and creating time-varying gravitational fields. Worse still are the hypervelocity stars. These are stars ejected from the galactic center by gravitational slingshot interactions with SGR-A star. When a binary star system ventures too close to the black hole, tidal forces can tear the binary apart. One star falls into a tighter orbit or directly into the black hole. The other star receives a gravitational kick that accelerates it to escape velocity and beyond. Hypervelocity stars have been observed travelling at up to 1,500 miles per second, fast enough to escape the Milky Way's gravity entirely. These stars are bullets fired randomly from the galactic center in all directions. Within the inner regions, hypervelocity stars are common. Estimates suggest dozens are produced every million years. On cosmic timescales, that is frequent. Encountering a hypervelocity star is catastrophic. At 700 miles per second, relative velocity between your spacecraft and the star could exceed 2,000 miles per second. At that speed, you have seconds of warning before collision. Avoidance requires thrust capabilities no realistic spacecraft possesses, and even a near miss is deadly. The star's gravity well extends millions of miles. Passing through it at high speed subjects your spacecraft to accelerations measured in hundreds of Gs. Structure fails, systems collapse, crew dies from deceleration trauma. Beyond the stars themselves, stellar remnants litter the region. White dwarfs, neutron stars, and stellar mass black holes orbit S-Gray star in large numbers. These objects are small, typically just miles or tens of miles across, making them nearly impossible to detect until you are dangerously close. But their gravity is intense. A neutron star contains more mass than the Sun compressed into a sphere the size of a city. Its surface gravity exceeds 100 billion Earth gravities. Passing within a few thousand miles of a neutron star produces tidal forces strong enough to shred spacecraft. The object is so small and so gravitationally intense that it acts as a point mass hazard. You cannot see it until you're almost on top of it, and by then, gravity has already locked you into a death spiral. Astronomers have detected several dozen neutron stars and stellar mass black holes within the central 10 light years, but detection is difficult. These objects emit little light. They reveal themselves primarily through X-ray emissions when they accrete matter, or through gravitational lensing when they pass in front of background stars. Most remain undetected. The true population could be hundreds or thousands. Therefore, the galactic centre is not empty space punctuated by occasional stars. It is a dense stellar environment where collisions happen regularly, where hypervelocity projectiles fire randomly, where invisible compact objects lurk in the darkness, and where gravitational chaos makes navigation impossible. This is a war zone, and you are not armoured against it. But even if you threaded the needle between stars, avoided hypervelocity projectiles, and somehow navigated the gravitational chaos, you would still be blind. Because the space between the stars is not empty. It is filled with dust and gas so thick that visible light cannot penetrate. You're about to enter a fog that hides the battlefield completely. The galactic centre is invisible, not because it is dark, but because dust blocks every wavelength of light the human eye can perceive. Between Earth and Sqa star lies a curtain of interstellar material so dense that optical extinction exceeds 30 magnitudes. That number means visible light is reduced by a factor of 1 trillion. For every trillion photons entering the dust cloud, one emerges. The rest scatter, absorb, or get re-emitted at different wavelengths. This is not ordinary dust. Interstellar dust consists of microscopic grains, mostly carbon and silicates, ranging from nanometers to microns in size. These grains form in the atmospheres of dying stars and get dispersed into space by stellar winds and supernova explosions. Over time, they accumulate in molecular clouds, vast regions of cold, dense gas where star formation occurs. The galactic centre hosts some of the largest molecular clouds in the Milky Way. The central molecular zone, a ring-shaped structure roughly 1,500 light-years across, contains tens of millions of solar masses of gas and dust. This material orbits Escarus star in a chaotic swarm, colliding and merging and fragmenting continuously. The density in some regions exceeds 10,000 particles per cubic centimetre, roughly 100,000 times denser than the interstellar medium near Earth. At these densities, dust grains are everywhere. The spacing between grains drops to meters or less. For a spacecraft travelling at even moderate velocities, this becomes a sandblasting environment, except the sand is moving at you at kilometers per second. Relative velocity determines impact energy. A dust grain 1 micron across, roughly the size of a bacterium, has a mass of about 1/1,000,000,000th of a gram. At 10 kilometers per second, typical for orbital velocities near the galactic centre, this grain carries kinetic energy equivalent to a small firecracker. When it strikes your hull, it vaporizes instantly, releasing that energy as heat and shock waves. The impact site reaches temperatures of tens of thousands of degrees, metal ablates, coatings burn away, a single grain does negligible damage. But you're not encountering single grains. At 10,000 particles per cubic centimetre and 10 kilometers per second, your spacecraft sweeps through roughly 100 billion particles per second per square metre of frontal area. That is 100 billion micro-explosions every second hammering your hull. The cumulative effect is erosion. Over hours, surface layers ablate away. Over days, hull thickness decreases measurably. Over weeks, structural integrity fails. The spacecraft does not puncture cleanly. It wears down like metal under a grinding wheel until weak points develop and catastrophic failure occurs. Shielding helps but cannot eliminate the problem. Whipple shields, multiple thin layers separated by gaps, work by vaporizing incoming particles on the first layer and spreading the resulting plasma cloud across subsequent layers. This reduces the energy density of impacts, but Whipple shields are designed for meteoroid impacts in near-Earth space, where particle velocities are a few tens of kilometers per second, and densities are measured in particles per cubic kilometer, not per cubic centimeter. At galactic center densities, Whipple shields erode as fast as primary hulls. The outer layers ablate continuously. Replacement becomes necessary after days of flight. No realistic mission can carry enough shield mass to survive months of transit through the central molecular zone. Larger particles pose even greater threats. Dust grains follow a size distribution. Most are submicron, but a significant fraction reach 10 microns. A few reach 100 microns. These larger grains carry proportionally more kinetic energy. A 100-micron grain at 10 kilometers per second hits with the energy of a rifle bullet. It does not just ablate surface material. It punches through thin sections. It fractures viewports. It penetrates pressure vessels. Therefore, flying through the central molecular zone is like flying through a shooting gallery where bullets arrive from all directions at once and continuously. There is no armor thick enough, no shield configuration adequate. The environment grinds down everything it touches. But kinetic damage is only one problem. The dust also blinds you. Visible light cannot penetrate, but neither can most other wavelengths. Ultraviolet light scatters off dust grains efficiently. Infrared light penetrates better, but still suffers significant extinction. Only radio waves and very long wavelength infrared pass through relatively unimpeded. This means navigation by visual means is impossible. You cannot see stars. You cannot see Scree Star until you're within a few light years. You cannot identify hazards until you are almost on top of them. Radar helps, but radar range is limited by the inverse square law. A radar powerful enough to detect objects at useful distances would consume enormous power and generate waste heat that becomes its own problem. The dust also creates a thermal trap. Spacecraft generate heat from onboard systems, engines, power reactors. In normal space, this heat radiates away as infrared, but in the central molecular zone, your own infrared radiation scatters off surrounding dust and gets absorbed by nearby gas. The environment is optically thick. Heat cannot escape efficiently. This forces reliance on active cooling. Radiators must be oversized. Coolant loops must handle higher thermal loads. Power requirements increase, and if cooling systems fail, internal temperatures rise rapidly. Electronics overheat. Life support fails. The spacecraft becomes an oven cooking itself from the inside. Gas poses additional problems. The central molecular zone contains not just dust, but also vast quantities of hydrogen, helium, and heavier elements in molecular form. Hydrogen molecules, carbon monoxide, ammonia, methanol, all exist in substantial concentrations. At the densities present, these molecules collide frequently with any surface they encounter. Each collision transfers momentum. At 10 kilometers per second, the cumulative drag from molecular collisions becomes measurable. Spacecraft decelerate continuously unless engines fire to compensate. Fuel consumption increases, mission duration decreases, and the drag is not uniform. Different regions have different densities. Your trajectory bends unpredictably as drag varies. The gas also corrodes. Many molecules in the interstellar medium are chemically reactive. Atomic oxygen, present in significant quantities near regions of active star formation, oxidizes metal surfaces. Hydroxyl radicals attack organic compounds. Over time, external components degrade, seals fail, lubricants break down, moving parts seize. But the most insidious aspect of the dust curtain is how it distorts perception. Infrared observations of the galactic center show structure that is invisible at other wavelengths. Filaments of warm dust, bubbles blown by stellar winds, shock fronts from supernova remnants. These structures move and evolve on timescales of years. What appears to be empty space in one observation contains a dense cloud in the next. This variability makes mapping impossible. Charts become obsolete before missions can use them. Pilots must navigate in real time based on sensor data that shows only the immediate vicinity. Long-range planning is impossible. You fly blind through a fog that hides stars, conceals hazards, and changes constantly. Astronomers overcome this blindness by observing at radio wavelengths. Radio waves, with wavelengths measured in centimeters or meters, diffract around dust grains and penetrate the central molecular zone with minimal extinction. This is how Scree Star was discovered and how its properties have been measured. Radio telescopes see through the dust. But radio imaging requires enormous antennas or arrays of antennas spread over large areas. A spacecraft cannot carry such equipment. Onboard sensors are limited to short baselines and therefore poor resolution. You can detect Scree Star's radio emission, but resolving structure around it requires precision you do not have. Therefore, the dust curtain ensures that any approach to the galactic center is a journey into darkness. You cannot see where you're going. You cannot identify threats until seconds before impact. You cannot navigate by landmarks because there are no visible landmarks. And all the while, your hull erodes under relentless particle bombardment, your systems corrode from chemical attack, and your heat builds because thermal radiation cannot escape. The environment is not just hostile, it is opaque, and flying blind through a battlefield is suicide. But even if you cleared the dust, even if you somehow reached Scree Star with hull intact and systems functional, time itself would betray you. Because gravity near the black hole does not just bend space, it bends time, and what seems like hours to you becomes centuries for everyone else. You're about to enter a prison where time is the bars. Time is not absolute. Near Esquerra star, this fact stops being a theoretical curiosity and becomes a cage. Einstein's general relativity predicts that gravity slows time. The stronger the gravitational field, the slower clocks tick. Near a supermassive black hole, this effect becomes extreme. Time dilation near the event horizon approaches infinity. 1 second for you becomes years, centuries, millennia for observers far from the gravitational well. The mathematics are precise. Time dilation factor depends on gravitational potential. At a distance where escape velocity equals half the speed of light, time runs at roughly 87% of the rate far from the black hole. Every hour you experience corresponds to 1 hour and 9 minutes for distant observers. The difference seems small, but as you descend closer, the effect amplifies rapidly. At a distance where escape velocity reaches 90% of light speed, time runs at 44% of the distant rate. 1 hour for you equals 2 hours and 16 minutes elsewhere. At 99% of light speed, time runs at 14% of normal. 1 hour becomes 7 hours. At 99.9%, 1 hour becomes 22 hours. The progression is not linear, it is exponential, approaching infinity as you approach the event horizon. At the event horizon itself, time dilation becomes infinite. 1 second at the horizon corresponds to infinite time elsewhere. This creates a bizarre situation. From your perspective falling toward the horizon, you cross it in finite time. You reach the boundary and pass through. But from the perspective of distant observers, you never cross. They watch you slow down, redshift and fade, asymptotically approaching the horizon but never quite reaching it. You appear frozen at the boundary forever. This is not just theoretical. Astronomers have observed time dilation effects in matter orbiting close to black holes. Accretion disk emissions show spectral features that are redshifted and broadened by gravitational effects. The inner edge of the disk, where matter orbits closest to the event horizon, shows the strongest time dilation. Light from that region is shifted to longer wavelengths by factors approaching 2. The photons are climbing out of a gravitational well so deep that they lose half their energy escaping. For a spacecraft approaching Esquerra star, time dilation becomes operationally significant well before reaching the event horizon. At 10 million miles out, roughly the distance of the innermost stable circular orbit, time runs at about 85%. A 1-year mission at that distance corresponds to 1 year and 2 months for everyone else. That sounds manageable until you consider what it means. You launch from Earth, you spend years in transit reaching the galactic center, you orbit Esquerra star for what feels like 1 year collecting data, you return home. Upon arrival, you discover that 15 months have passed on Earth. You have aged 12 months, everyone else has aged 15. The discrepancy seems small, but now consider a closer approach. At 1 million miles from the event horizon, within the photon sphere where escape becomes impossible, time runs at roughly 50% of distant rates. 1 year for you equals 2 years elsewhere. A decade-long mission becomes 20 years for Earth. Crew members return to find their children grown, their spouses aged, their world changed. They have not travelled to another place. They have travelled to another time. This effect is not science fiction, it is measured physics. GPS satellites in Earth orbit experience time dilation of about 38 microseconds per day due to Earth's gravity and their orbital velocity. The effect is small but measurable. GPS systems must correct for it, or position calculations drift by miles per day. Near Esquerra star, the effect is not microseconds. It is hours, days, years. But the operational problems go deeper than simply aging at different rates. Time dilation affects communication. Radio signals sent from near the black hole to distant observers are redshifted by gravitational effects. Frequency decreases, wavelength increases. A signal transmitted at 1 GHz might be received at 500 MHz if transmitted from deep within the gravitational well. This frequency shift complicates receiver design. You must anticipate the exact amount of redshift to tune receivers correctly. But redshift varies with distance from the black hole. As your spacecraft maneuvers, changing altitude, the redshift changes. Receivers must track a moving target. Data rates suffer. Error rates increase. Worse, time dilation affects the rate at which signals are received. 1 second of transmission from deep in the gravitational well arrives stretched over 2 seconds or more at a distant receiver. The data rate is effectively cut in half. Bandwidth drops. Communication becomes sluggish. Real-time control from Earth is impossible. Commands sent take years to arrive, and responses take years to return, and the responses are slowed further by time dilation. Therefore, any mission near a star must be autonomous, pre-programmed, unable to adapt to unforeseen circumstances because there is no way to get updated instructions in useful time. The spacecraft operates alone, cut off from support, executing commands determined years earlier based on predictions that may no longer be accurate. The psychological impact is severe. Crew members, if any exist, face the knowledge that they are falling out of sync with everyone they know. Every hour spent near the black hole is an hour they lose relative to home. Friends age, family dies, the world moves on without them, and there is no reversing it. Time dilation is not a temporary effect that ends when you leave. The time you lose is gone permanently. This creates a one-way door. You can descend into the gravitational well, but returning means emerging into a future you did not live through. The deeper you go, the farther forward you jump. At extreme proximity to the event horizon, even brief visits correspond to decades or centuries passing outside. You could spend one day at the photon sphere and return to find Earth has aged 100 years. This is not time travel in the conventional sense. You cannot visit the past. You can only skip forward, losing time irreversibly. And unlike time dilation from high-speed travel, which affects both directions equally, gravitational time dilation is asymmetric. Descending into the well costs you time. Climbing back out does not restore it. The effect creates strategic impossibilities. Any civilization attempting to study a star closely must accept that researchers will be temporarily displaced from the society that sent them. They will return to a world that has moved on. Technologies will have advanced. Political situations will have changed. Languages may have drifted. The researchers become time refugees, exiled not to another place but to another era. Some have proposed using this effect deliberately. Send someone into a deep gravitational well for subjectively short time, and they emerge far in the future. It is a crude form of forward time travel, but the cost is isolation. You cannot return to your own time. You can only watch from the future as history records what happened after you left. Near a star, this time prison operates automatically. Gravity does not ask permission. It does not provide warnings. It simply distorts space-time, and time dilation is the inevitable consequence. The closer you approach, the more time you lose, and there is no technology that can prevent it. Time dilation is not something that happens to you. It is something that happens to space-time itself. You are simply along for the ride, but time dilation is passive. It does not actively destroy. It simply separates you from the rest of the universe temporally. The next threat, however, is violently active, because between you and the event horizon lies a rotating disk of matter so hot, so energetic, and so lethal that it makes every previous hazard look gentle. You're about to meet the accretion inferno. Matter does not fall straight into a star. It spirals. Gas clouds, shredded stars, dust, all carry angular momentum from their original orbits. As they fall inward, conservation of angular momentum forces them to spin faster. The material flattens into a disk, an accretion disk, orbiting the black hole at velocities approaching the speed of light. This disk is not solid. It is plasma. Temperatures reach millions of degrees. At these temperatures, atoms cannot exist. Electrons are stripped from nuclei. What remains is a soup of charged particles, protons and electrons moving independently, colliding constantly, radiating energy across the electromagnetic spectrum. The inner edge of the accretion disk sits at the innermost stable circular orbit for SGR A star. At this radius, matter orbits at approximately 30% of light speed, that is 56,000 miles per second. At such velocities, relativistic effects become significant. Mass increases, time dilates, lengths contract in the direction of motion, friction within the disk generates the heat. Plasma in inner orbits moves faster than plasma in outer orbits. The velocity difference creates shear. Particles collide. Kinetic energy converts to thermal energy. The disk heats from the inside out, with the hottest regions closest to the black hole. At the inner edge, temperatures exceed 10 million degrees Kelvin. This is hotter than the core of the Sun. At these temperatures, thermal radiation peaks in the X-ray spectrum. The disk glows not with visible light, but with high-energy photons capable of ionizing atoms and breaking molecular bonds light years away. The accretion disk around Escura star is currently dim by black hole standards. The black hole is not feeding actively. Infill rates are low, perhaps 1/1000th of an Earth mass per year. This starvation diet produces a faint accretion flow rather than a bright disk. But even this dim state radiates more power than thousands of suns. When Escura star feeds actively, consuming a gas cloud or torn star, the accretion rate increases by factors of millions. The disk brightens dramatically. X-ray luminosity spikes. The black hole becomes one of the brightest objects in the galaxy. This happened as recently as a few hundred years ago. Observations of light echoes, reflections of past outbursts bouncing off nearby gas clouds, show that Escura star was roughly 1,000,000 times brighter in the 17th century than it is today. For anything in the vicinity, an accretion flare is an extinction event. X-ray flux increases to levels that ionize gas across light years. Planets within 10 light years would have their atmospheres stripped. Any spacecraft within 1 light year would be cooked. Hull temperatures would rise to thousands of degrees within minutes. Electronics would fail. Crew would receive lethal radiation doses in seconds. But even the quiescent accretion flow is deadly at close range. Approaching the disk means entering a region where ambient temperature is measured in millions of degrees. There is no insulation against this. Heat transfer occurs through radiation. At these temperatures, every surface radiates intensely. Your spacecraft hull, even if it starts cold, begins absorbing thermal radiation from surrounding plasma. Temperature rises. Radiative heat transfer scales with the 4th power of temperature. Double the temperature, heat transfer increases by a factor of 16. At 1,000,000 degrees, radiative power is so intense that materials vaporize. Metals boil, ceramics sublimate. Even refractory materials like tungsten or carbon composites cannot withstand sustained exposure. The disk also emits particle radiation. Protons and heavier nuclei, accelerated by magnetic fields within the plasma, spray outward in all directions. These particles carry energies ranging from thousands to billions of electron volts. When they strike matter, they trigger nuclear reactions. Spacecraft hulls become radioactive. Neutron activation converts stable isotopes into radioactive ones. The hull itself becomes a radiation source, poisoning crew and degrading systems. Magnetic fields thread through the accretion disk, generated by the motion of charged particles. These fields are not uniform. They twist and tangle, forming loops and filaments that snap and reconnect violently. Magnetic reconnection events release enormous bursts of energy, accelerating particles to near light speed and generating X-ray flares. The disk is not static. It is dynamic, turbulent, constantly reconfiguring itself on timescales of hours or days. Therefore, flying through the accretion disk is not like flying through a cloud. It is like flying through a tornado made of fire. The environment changes unpredictably. Temperature spikes, radiation bursts, magnetic fields shift. There is no safe path, no stable trajectory. The disk is chaos operating at relativistic speeds and temperatures that vaporize matter on contact. But the disk's deadliest feature is not temperature or radiation, it is the jets. Perpendicular to the accretion disk, along the black hole's rotation axis, plasma jets erupt. These jets are driven by magnetic fields that extract rotational energy from the black hole itself through a process called the Blandford-Znajek mechanism. The fields act like wires connecting the black hole to the disk, allowing energy to flow outward. The jets accelerate plasma to velocities exceeding 99% of light speed. Material in the jets is compressed and heated to billions of degrees. Gamma rays dominate the emission spectrum. The jets extend for light years, sometimes for tens or hundreds of light years, before dissipating into the surrounding interstellar medium. For Escura star, the jets are currently weak because the accretion rate is low, but evidence suggests they were once much stronger. Structures in the surrounding gas, called the Fermi bubbles, extend thousands of light years above and below the galactic plane. These bubbles are thought to be remnants of past jet activity when Escura star was feeding heavily. The bubbles are filled with high-energy particles and glow in gamma rays. When active, the jets from Escura star would sterilize huge volumes of space. Anything within the jet cone would be vaporized instantly. Gamma ray flux within the jet exceeds anything supernova explosions produce. The beam is collimated, focused along a narrow angle, which makes it even more lethal. Intensity does not drop with distance as rapidly as it would for an isotropic source. The jet maintains killing power across light years. Predicting when jets will activate is impossible. They depend on accretion rate, which varies unpredictably as gas clouds and stars wander too close to the black hole. A jet could activate with hours of warning, or it could remain dormant for millennia. There is no way to know. Therefore, approaching a star means accepting the risk of sudden incineration. The accretion disk might flare, the jets might activate, and if either happens while you're within range, there is no escape. Light speed warnings mean you have zero time to react. By the time you see the flare begin, the radiation front is already upon you. The disk is a furnace, the jets are flamethrowers. Together they create a kill zone extending light years from the black hole. Nothing organic survives, nothing mechanical functions. Matter itself struggles to maintain coherence under the thermal and radiative assault. But even if the disk were cold and the jets dormant, the space immediately around the black hole contains another trap, the ergosphere, a region where space-time itself is dragged around the rotating black hole, where standing still becomes impossible, and where the very concept of a stationary reference frame breaks down. You're about to enter a whirlpool where even motionless objects must spin. A star rotates. The black hole spins on its axis at a significant fraction of the maximum rate allowed by physics. This rotation drags space-time itself around the black hole in a process called frame dragging. Within a certain distance, space-time rotates so quickly that nothing can remain stationary. This region is the ergosphere, and it represents a trap more subtle and more absolute than gravity alone. The ergosphere extends from the event horizon outward to roughly twice the horizon radius. For a star, this means the ergosphere reaches approximately 24 million miles from the center. Within this zone, space-time itself is in motion, not flowing like a fluid, but rotating like a solid structure, and everything within it must rotate along with it. This is difficult to visualize because it contradicts everyday experience. On Earth, you can stand still relative to the ground even though Earth rotates. You're not forced to move just because the planet spins. But near a rotating black hole, space-time itself is the thing that is moving. There is no external reference frame to stand still relative to. The grid of space and time is rotating, and you are embedded in that grid. The mathematics describe this through the metric of space-time. In flat, non-rotating space, the metric is simple. Space and time are independent. You can move through space without moving through time beyond the normal forward progression. But in the ergosphere, the metric contains off-diagonal terms that mix space and time. Moving through time automatically implies moving through space. Standing still in space would require moving backward in time, which is impossible. Therefore, everything in the ergosphere must orbit the black hole in the direction of its rotation. You cannot orbit against the rotation. You cannot hover. You cannot even orbit slowly. There is a minimum angular velocity you must have just to exist in that region. Below this velocity, your trajectory becomes physically impossible. For objects far from the ergosphere, frame dragging is negligible. Earth experiences frame dragging from the sun's rotation, but the effect is so tiny that it is measured in milliux seconds per century. Near a star, frame dragging dominates. The ergosphere rotates at velocities approaching light speed. Space-time at the outer edge of the ergosphere is dragged around at roughly 10% of light speed. At the inner edge, near the event horizon, the dragging velocity approaches 100%. This creates operational problems that have no solution. A spacecraft entering the ergosphere must accelerate to match the rotation of space-time. This requires thrust, enormous thrust. Maintaining an orbit within the ergosphere against perturbations requires continuous engine burns. Fuel consumption is catastrophic, and there is no equilibrium orbit, no trajectory that allows coasting. You must thrust continuously, or you spiral inward. But even continuous thrust may not be enough. The deeper into the ergosphere you descend, the faster you must orbit. At some point, the required velocity exceeds what chemical or even fusion rockets can provide. The exhaust velocity of your engines becomes insufficient. You cannot accelerate fast enough to maintain altitude. Gravity and frame dragging combine to pull you downward despite maximum thrust. This makes the ergosphere a one-way surface. You can descend into it by cutting engines and letting frame dragging accelerate you. But climbing back out requires delta-v that no realistic spacecraft can carry. The ergosphere is a pit with slippery walls. Once you slide in, you cannot climb out. The Penrose process offers a theoretical way to extract energy from the ergosphere. By dropping matter into the ergosphere in precisely calculated trajectories, you can split the matter into two pieces. One piece falls into the black hole, The other piece escapes with more energy than the original matter had. The extra energy comes from the black hole's rotational energy. You are stealing spin from the black hole. This process works in theory. Some astrophysicists believe that jets from black holes are powered by natural Penrose processes occurring in the ergosphere, but engineering a controlled Penrose extraction is beyond any conceivable technology. The trajectories must be calculated with absurd precision, timing must be exact, and the energy gain is modest compared to the risks. A small mistake and both pieces fall in. You lose the matter and gain nothing. Therefore, the Penrose process is not a useful escape mechanism. It is a theoretical curiosity that highlights how bizarre the physics of the ergosphere becomes. Energy can be extracted from rotation, but doing so requires manipulating trajectories in a region where space-time itself is a moving target. Frame dragging also affects light. Photons entering the ergosphere are dragged around the black hole. A beam of light aimed directly away from the black hole will curve. Instead of travelling in a straight line, it follows a curved path bending in the direction of rotation. This means you cannot shine a light outward and expect it to escape directly. The light curves. It orbits partially before escaping, if it escapes at all. This distorts vision in the ergosphere. Looking outward, you see images of distant stars smeared into arcs. Light from a single star reaches you along multiple curved paths, creating multiple images at different positions in the sky. The sky becomes a funhouse mirror where nothing appears where it actually is. Navigation by starlight becomes impossible. Your instruments see distorted images, positions are wrong, directions are unreliable. You must navigate by dead reckoning, trusting your inertial systems and integrating acceleration over time. But inertial navigation accumulates errors. Without external references to correct against, your position estimate drifts. You lose track of where you are. The ergosphere also creates a peculiar gravitational effect. Because space-time is rotating, angular momentum is not conserved in the usual way. Objects in the ergosphere can gain or lose angular momentum through interactions with the drag space-time. This violates intuition. Normally, angular momentum is conserved unless external torques act. But in the ergosphere, the rotating space-time itself acts as a reservoir of angular momentum. You can exchange angular momentum with the black hole by simply existing in the ergosphere. This means trajectories are not deterministic in the usual sense. Small perturbations, interactions with infalling matter, magnetic fields, can alter your angular momentum in ways that would be impossible in normal space. Your orbit changes unpredictably. Predictions become unreliable. Chaos dominates. Therefore, the ergosphere is a trap that operates through geometry rather than force. It does not pull you in with overwhelming gravity, though gravity is certainly present. It traps you by removing the possibility of stationary existence. You must move, you must orbit, and once you are orbiting deep within the ergosphere, you cannot generate enough thrust to escape. The geometry of space-time itself has become a prison. But the ergosphere is not the final horror. There is something stranger, something that occurs on quantum scales where the distinction between particles and vacuum blurs. The black hole emits radiation, not from inside the event horizon, but from just outside it. And this radiation, faint though it is, represents a slow but inevitable destruction of the black hole itself. You're about to confront the quantum betrayal, where black holes are not eternal after all. Black holes evaporate. This prediction, made by Stephen Hawking in 1974, contradicts everything classical physics says about black holes. General relativity insists that nothing escapes an event horizon, but quantum mechanics introduces a loophole. Virtual particle pairs, constantly appearing and annihilating in empty space, can be separated by the event horizon. One particle falls in, the other escapes. The escaping particle is real. It carries energy, and that energy must come from somewhere. It comes from the black hole's mass. This is Hawking radiation. For SGR star, the effect is absurdly weak. The temperature of Hawking radiation scales inversely with black hole mass. Supermassive black holes are cold. SGR star radiates at a temperature of roughly 1/10 millionth of a Kelvin. This is far colder than the cosmic microwave background, which sits at 2.7 Kelvin. The black hole absorbs more energy from the cosmic microwave background than it emits through Hawking radiation. It is growing, not shrinking. But the universe is expanding. The cosmic microwave background is cooling. In roughly 100 trillion years, the background temperature will drop below SGR star's Hawking temperature. At that point, the black hole will begin losing mass, slowly, imperceptibly, but inevitably. The evaporation rate accelerates as the black hole shrinks. Smaller black holes have higher Hawking temperatures and radiate faster. A black hole with the mass of SGR star will take approximately 10 to the 94th years to evaporate completely. That number is so large it defies comprehension. The current age of the universe is roughly 10 to the 10th years. SGR star will outlast the stars by factors of 10 to the 80. But eventually it will evaporate. The final stages will be violent. As the black hole shrinks to stellar mass, then planetary mass, then smaller, Hawking radiation intensifies. The black hole heats up. It glows. In its final second, a black hole radiates with the power of billions of nuclear bombs. Then it vanishes. The event horizon disappears. The singularity, if it still exists in any meaningful sense, is exposed briefly before disintegrating into a burst of radiation and particles. This endpoint is so far in the future that it is irrelevant to anything happening now. But it reveals a profound truth. Black holes are not eternal. They are temporary structures. They will all evaporate given enough time. The universe's ultimate fate includes a period where black holes are the last remaining massive objects, slowly radiating away into the void, and then even they will be gone. Hawking radiation introduces a deeper problem, the information paradox. Quantum mechanics insists that information cannot be destroyed. The state of a system at one time determines its state at all future times if you know the laws of physics. But black holes seem to destroy information. Throw a book into a black hole. The book's information, the arrangement of atoms, the text on pages disappears behind the event horizon. When the black hole eventually evaporates, the radiation it emits is thermal, random. It contains no information about what fell in. This creates a contradiction. Quantum mechanics says information is preserved. Black hole thermodynamics says information is destroyed. One of these principles must be wrong, or our understanding of what happens at event horizons is incomplete. Proposed solutions involve exotic physics. Some suggest information is encoded in subtle correlations within Hawking radiation, correlations so delicate that they are effectively invisible but technically present. Others propose that information is stored on the event horizon itself, in a two-dimensional structure called a hologram, and released slowly as the black hole evaporates. A third option is that information escapes through quantum tunneling, or wormholes connecting the black hole interior to distant regions of space. None of these solutions are proven. The information paradox remains unresolved, and its implications are disturbing. If information can be destroyed, then the universe is not deterministic. The future is not uniquely determined by the present. Predictability breaks down at a fundamental level. Alternatively, if information is preserved but in ways we do not understand, then black holes are far stranger than general relativity suggests. They are quantum objects obeying rules we have not yet discovered. For anything falling into SGR star, the information paradox is more than academic. Your information, the quantum states defining every particle in your body, crosses the event horizon. From an external perspective, that information is lost. It smears across the horizon and eventually radiates away as structureless thermal radiation over 10 to the 94th years. You are erased not just physically, but informationally. The universe forgets you existed. This erasure is absolute in a way that ordinary death is not. When you die normally, your atoms persist. They scatter and recombine into new structures. The information defining you is scrambled but not destroyed. It exists in diffuse form, spread across the environment. Given perfect knowledge of the universe's state and infinite computational power, you could theoretically reconstruct what you once were. But information that crosses an event horizon is gone in a way that may be fundamentally irretrievable. Even with infinite computational power, even with perfect knowledge of everything outside the black hole, you cannot reconstruct what fell in. The information is not hidden. It is destroyed, or at minimum rendered inaccessible by the structure of space-time itself. This is the quantum betrayal. Classical physics says black holes are eternal prisons that trap matter forever. Quantum mechanics says black holes evaporate and information is lost. Either way, you do not escape. Either you are trapped eternally or you are erased from existence as the black hole slowly radiates away your constituent particles as random thermal photons. Hawking radiation also has practical implications for the far future. In the unimaginably distant era when black holes dominate the universe, Hawking radiation will be the primary energy source. Civilizations, if any still exist, might cluster around black holes to harvest the faint trickle of radiation. They would live in a universe lit only by the dim glow of evaporating black holes, waiting out the incomprehensible ages until even those fade. But for Zurastar now, Hawking radiation is irrelevant to survival. The effect is too weak to measure. The black hole's gravity, radiation environment, tidal forces and frame dragging will kill you billions of years before Hawking radiation becomes significant. The quantum betrayal is a distant threat. The immediate threats are classical and overwhelming, yet Hawking radiation represents the ultimate fate of Zurastar and every black hole. They are not forever, they are temporary, and their evaporation erases everything they consumed, returning it to the universe as featureless thermal radiation. The black holes are not just destructive, they are erasers, removing structure and information from reality and replacing it with formless heat. But even Hawking radiation, strange and slow as it is, does not represent the deepest horror. That honor belongs to what lies beyond the event horizon, because once you cross that boundary, the rules change completely. Space and time exchange roles. The future points toward the singularity. Escape requires traveling backward in time, which is impossible. You're about to confront the causality breakdown where physics itself ends, and the universe gives up trying to make sense. Cross the event horizon, and the universe stops obeying rules you understand. Outside, the future is open. Multiple trajectories are possible. You can go left, right, forward, back. But inside, there is only one direction, toward the singularity. Not because gravity pulls you there, though it does, but because the geometry of space-time inside the horizon makes the singularity your future. Not a place you might go, a time you will reach. This is the causality breakdown. Outside the event horizon, space is space and time is time. Radial distance is a coordinate you can move along in either direction. Time flows forward. Inside, these roles reverse. The radial coordinate becomes time-like. The singularity is not a location at the center of the black hole. It is a moment in your future, an endpoint in time that you will reach approximately 1/10,000th of a second after crossing the horizon for Zurastar. You cannot avoid it. Firing your engines does not help. Changing direction does not help. The singularity is not something you move toward through space. It is something you move toward through time. Avoiding it would require stopping time or reversing it. Neither is possible. General relativity describes the interior through the Schwarzschild metric for non-rotating black holes, or the Kerr metric for rotating ones like Zurastar. Both metrics show the same fundamental feature. Inside the horizon, all future-directed time-like paths terminate at the singularity. There are no exceptions. No matter how you accelerate, no matter what trajectory you follow, you reach the singularity within finite proper time. Proper time is the time you experience. For Zurastar, this interval is roughly 10,000 microseconds. You have 10 milliseconds from horizon crossing to singularity impact, 10 milliseconds to exist inside a region where physics breaks down completely. What happens during those 10 milliseconds? Tidal forces intensify. The difference in gravitational pull between your head and feet grows without bound. As you approach the singularity, space-time curvature approaches infinity. Tidal acceleration becomes infinite. You're stretched to infinite length and compressed to zero width. This is spaghettification taken to its logical extreme. You do not just elongate, you become infinitely thin. But this description is misleading because it assumes your body remains intact long enough to reach the singularity. It does not. Tidal forces exceed molecular bond strength within microseconds of crossing the horizon. Your body disassembles into atoms within the first millisecond. Those atoms ionize and shred into elementary particles within the next few milliseconds. By the time you reach the singularity, you're not matter in any conventional sense. You're a stream of elementary particles, quarks and electrons, compressed and stretched beyond recognition. The singularity itself is a boundary where general relativity fails. Space-time curvature becomes infinite. Density becomes infinite. Temperature, if the concept still applies, becomes infinite. The equations produce infinities, which is physics' way of admitting it does not know what happens. Infinities in physical theories signal breakdowns. They indicate missing physics. Something else must take over, but we do not know what. Quantum gravity, the as yet undiscovered theory that unifies general relativity with quantum mechanics, should describe the singularity. But we do not have that theory. String theory, loop quantum gravity, and other candidates make predictions, but none are confirmed. The singularity remains a mystery, a place where the universe's rules end. Some physicists suggest the singularity is not a point but a chaotic region where space-time fluctuates wildly at quantum scales. Others propose it is a gateway to other regions of space-time, a wormhole connecting to a white hole in another universe. Still others argue that quantum effects prevent singularity formation entirely, replacing the infinite curvature with a finite but extremely high curvature region. None of these ideas help you. Whether the singularity is a point of infinite density or a quantum foam or a wormhole, the outcome is the same. You do not survive. The extreme curvature and tidal forces destroy any structure. Information about what you were is scrambled beyond recovery or lost entirely. You cease to exist as an organized entity. But the singularity is not the only horror inside the horizon. The Kerr metric for rotating black holes predicts additional features: the Cauchy horizon, the inner horizon, regions where causality becomes even more damaged than at the singularity. The Cauchy horizon sits inside the event horizon. It is a surface beyond which predictability fails completely. Outside the Cauchy horizon, even inside the event horizon, the equations of general relativity still produce unique solutions. Given initial conditions, you can calculate what happens next. But beyond the Cauchy horizon, uniqueness breaks down. Multiple futures become possible from the same initial conditions, or no future is possible. The equations stop giving answers. This happens because the Cauchy horizon is a place where information from the outside universe piles up. Due to time dilation, signals from the external universe that were emitted at different times all arrive at the Cauchy horizon simultaneously from the perspective of infalling matter. The entire infinite future of the external universe floods in at once. The energy density becomes infinite. Space-time curvature becomes infinite. The Cauchy horizon is a singularity of its own, possibly more violent than the central singularity. Whether the Cauchy horizon exists in real black holes is debated. Some calculations suggest quantum effects or instabilities destroy it before it can form. Others suggest it remains but is hidden behind the event horizon, where it cannot affect the external universe. Either way, anything falling through it is annihilated by infinite energy density. The interior of Esgara star is not empty space with a singularity at the center. It is a region where space-time geometry is so distorted that concepts like distance, duration, and causality lose meaning. You cannot map it. You cannot navigate it. You cannot survive it. Some have speculated about what an observer would see while falling toward the singularity. Outside the event horizon, looking back, you would see the universe blue-shifted and accelerated. Time outside appears to speed up due to gravitational time dilation working in reverse from your perspective. Stars evolve rapidly. Galaxies merge in fast-forward. If you could survive long enough, you would watch the universe age billions of years in seconds. But inside the horizon, this view is cut off. Light from outside can still reach you because photons can fall inward, but the light is increasingly redshifted and dimmed. The universe fades. Darkness closes in. The only light comes from Hawking radiation emitted near the horizon, a faint glow that does nothing to illuminate the interior. Looking toward the singularity, if you could see it, would reveal nothing comprehensible. Light emitted from near the singularity is gravitationally redshifted to infinite wavelength. It becomes invisible. The singularity is cloaked in darkness not because it does not emit light, but because the light is redshifted out of existence before it can travel any distance. Therefore, falling into Sesgara star is a journey into darkness, a descent into a region where time and space trade places, where causality breaks, where physics ends, and where annihilation is not just probable but guaranteed by geometry. The event horizon is not a surface. It is a point of no return defined by mathematics. Once you cross it, your future is determined. You will reach the singularity. You will be destroyed. There are no alternatives. This is why the galactic center must remain forbidden. Not because we lack the technology to reach it, though we do. Not because the journey is dangerous, though it is. But because the center of the galaxy contains a region where the universe itself stops functioning, where the laws of physics break down, where existence becomes impossible. The black hole is not a place. It is an ending. And everything that approaches it shares the same fate. Radiation strips you. Tidal forces shred you. Time traps you. The accretion disk incinerates you. The ergosphere captures you. The event horizon erases you. And the singularity obliterates you. But this final truth reveals something deeper about why we must never go there.